The idea of electron location. Where are they? How do we represent where they are? We got this marble in the baseball stadium thing going on. And we've got this idea about energy being quantized. And so this section here tries to bring these two things together and think about the nature of those electrons. In fact, we're going to end up giving them an address, just like your home has an address, and that address sort of tells us everything about those electrons in terms of where they are and their general characteristics. You certainly, the early studies and the photoelectric effect in particular underscored the idea that these electrons must exist at discrete energy levels. The idea that if the frequency of incident radiation was sufficient, the electrons would be ejected from their location, and if it were sufficient, they wouldn't be. And it was also fairly obvious that our simple portrayal of these electrons as moving around the nucleus like the planets move around the sun was not an especially accurate portrayal either. And so off we go. The first sort of cementing evidence came in the form of what we call emission spectra from various elements. The idea here is that you take an element, you vaporize it, you put it in a vacuum tube and you run an electrical current through it, and that electrical current causes then the electrons to get excited, and in the process they jump up and down energy levels and emit energy that we can then measure in terms of the radiation that comes off. The idea then that when the electron is in a ground state, it is at the lowest possible energy, and that if we give the atom energy, the electrons move to higher, sometimes called excited states, and then when we remove the source of energy, the electrons then cascade back down to their ground state. And as we're going to see, the line emission spectrum for hydrogen, which is of course the simplest atom with the fewest number of electrons and hence the fewest number of possible energy conditions, illustrated this idea very nicely. Here it is, the classic experiment going back almost 100 years now, I believe, of where the element here in this discharge tube connected to a high voltage circuit glows a vivid pink color. The light is then focused in through a slit and a prism where, as you have probably seen, the different colors are separated, and those colors then were lines on this spectrum where only certain colors were produced from this excited hydrogen atom, this, of course, collection of excited hydrogen atoms. You can now sort of begin to understand that if the energies of the electrons in those excited hydrogen atoms were continuous, that the projection would be the rainbow with no gaps in between, But because the emission is concentrated in only a few wavelengths, we have to conclude that the energies of the electrons can only be certain quantities. And this line emission spectrum, which by the way is characteristic of all elements, more or less proves that the energy of those electrons has to be quantized. Only certain energies are available, and the electrons then, when excited, move up. When they return to the ground state, off we go, and this line emission spectrum then distinctive. Say as an aside, this is one technique for identifying elements. That is to say, a mystery sample is brought in, vaporized, we look at the line emission spectrum and we can make a correspondence with the element. Each element has a unique line emission spectrum. The idea here then, in terms of the Bohr model of the atom and this hydrogen line emission spectrum, is that the energies of the electrons are fixed at certain levels. In this instance, we can pretend that this is the nucleus. Notice I've drawn these as circles, but they're not. I'm just representing them as the simplest possible situation, and that these then represent the different energy levels. I'm only showing 3 to keep the diagram small, that that electron can take. The electron, if we represent it as a little dot, in its ground state would be at energy level 1. Look at your periodic table. Hydrogen is in the first period. The period now corresponds to energy level. If we energize that electron by providing it with just the right amount of energy, we can cause it to jump either to energy level 2 or energy level 3, or of course if we give it enough energy, we can cause it to be stripped altogether out of that atom. But let's stick with these two possibilities. The energy level then of the electron starts here at the lowest possibility. It's not a very good diagram. I'll try that again. And as we give it more and more energy, we can cause it to jump up to the various energy levels. But it's just like a set of stairs in that when this electron returns down to its ground state, it has to emit only certain amounts of energy represented by the lines here. That is to say, when that electron goes back from energy level 3 to energy level 1, a distinctive amount of energy is emitted and corresponds to one of those lines on the line emission spectrum. Here, another diagram showing the same basic idea where the return of the electron to its ground state is accompanied by the emission of a photon that has exactly the amount of energy that is represented by that returning electron. Remember that E equals hB. Here is the energy lost by the electron, and it's converted into a photon with a given frequency, which of course we can measure, corresponds to a given wavelength, which then of course represented by that line emission spectrum. And so using this model, we can actually predict, describe, assign an energy to a particular electron in a particular atom. The revelations arrive hot and heavy and furious in terms of their number. This is an extremely fertile period in the history of science, when the 1920s, as more and more scientists begin to understand the quantum nature of the atom. Just some names and some general milestones. De Broglie, an important player in this whole thing, talks about the wave-particle duality of light as well as the wave-particle duality of matter, and assigns wavelengths to pieces of matter as well as quantum energies to pieces of light. So light has particle-like properties, matter has wave-like properties, but these very strange properties do not really show up at the macroscopic scale, but rather only appear at that atomic scale. And you may have heard or read or at some point become aware that there is a distinct disconnect between physics that explain the macro world and the physics that explain this micro world, this quantum world, that we still have not fully reconciled. The uncertainty principle proves to be hugely important and opens the door to an entirely different view of the world, in the sense that now it is a completely probabilistic view. It is impossible to locate an electron definitively. In point of fact, locating it changes its behavior, and so it becomes a trade-off, that there is an inherent uncertainty, and this then results in our representation of the electron as a sort of amorphous cloud, wherein, if you want to think of the electron as a point charge, the electron is moving throughout that space. Or if you want to think about it as a wave phenomenon, the electron is moving as a wave, if you will, in that basic physical space. And there is only, in fact, a probability of its location, not certainty. Perhaps Edwin Schrödinger, the most famous of the scientists who emerged from that period, and he derives a very mathematically powerful and elegant quantum theory with equations that describe both the energy levels as well as the shapes of the space that the electrons evolve in, and opens the door then to this exciting new view of the subatomic world. Unfortunately, the Schrodinger equations are very, very complex, and so we never really address them directly, but we do use one of their products, the quantum numbers, to assign addresses, locations to electrons. We'll pick that up in the next video.